Hello everyone and good afternoon to this afternoon session on aerodynamics. We are scheduled to have 3 speakers in this session. The first is to be Mr. Mohammed Najman, our second speaker, Dr. Zeben Lin, and our third speaker is to be Professor Mario Tomei. At this point in time, we just have one of our 3 speakers present. So we're going to start with the second scheduled speaker, Mr. Lin. And Mr. Lin is joining us from Manchester Metropolitan University. And he's going to present on the performance of OpenFOAM overset mesh solver for modeling offshore wind turbine rotor aerodynamics. So at this point, I'll hand over to Dr. Lin, and I will join you later.
Yeah, thanks for your introduction. So I'm going to share my screen. Here's my slides. So can you see my slides full screen?
Yes, yep, they look good.
Thank you. My name is Zeben Lin, and I'm currently a research associate in the Center of Mathematical Modeling and Flow Analysis Group Center and in Manchester Metropolitan University. So today I'm going to introduce the presentation on the title on the performance of overset mesh solver in OpenFOAM and on aerodynamics of an offshore wind turbine rotor. So as you may know, with increasing demand of renewable energy, so floating offshore wind turbine has been one of the most popular renewable energy devices in the ocean. And wind resources has been constant resources and clean resources around the world. And in the UK, there's many policy, like national policies for developing such renewable energy in the UK. So our project is funded by EPSRC, and then the objective of our project is to develop integrated aerodynamics and hydrodynamics model for the offshore floating wind turbine, and for predicting the vertical life and optimizing power control system, and estimating the survivability and stability during its operation. So there are many low fidelity numerical models such as FAST and some low order numerical model based on the blade element methods. So in this project, we aim to developing a high fidelity numerical model for simulating both aerodynamics and hydrodynamics simultaneously. So here's this geometry generated by Salom software. So you can see the red the rotor and the floater is highlighted in red. So the transparent boxes or the body fixed geometry is the overset zone we attempt to use in a numerical simulation. So I will give you preliminary results of our code development in the end of our presentation. So for the aerodynamics, we used OpenFOAM to simulate the rotated blades in the wind in a constant wind speed. So I think everybody will be very familiar with Kelvin equations here, with the Navier-Stokes equation and the mass conservation equation and the momentum conservation equation. Then the turbulence model, where we used K omega shear-stress transport. So I'm not going into details of this turbulence model. At present, we haven't tested any other turbulence models such as K epsilon or large eddy simulation, but that will be one of our missions in the future to test the sensitivity on the turbulence model. So this section, I'm going to introduce the model setup with snappy Hex Mesh in OpenFOAM. So there are 2 model setups here. So the first is based on the circular disk as showing in the screenshot here. There are big circular disks to cover the whole blades, the 3 blades here, and the background mesh is based on the mesh density of background mesh is then based on the mesh density in the circular disk instead of the mesh around the blade. So the second one is the body fitted zone used to cover the blades here with a limited area, like for example in a circular disk there are some abundant area not used for offset zone, but this abundant zone can be used for interpolations from the background mesh into the offset mesh zone. So because of the use of a body fitted zone, so the overall mesh number of background mesh used in the body fitted zone here is much larger than the background mesh in the circular disk case, because the mesh around the blades is around the blades in the body fitted zone is very well refined in order to capture the details such as a trailing edge and of the blade, and there are some surface refinement has been added in both cases. So the white plus in 2 cases are slightly different. You can see from the right panel of the screenshot, 2 screenshots here. The red zone and the red zone indicate the overset zone used in a model simulation, and the blue, the thick blue or blue zone is the background mesh, and so the shape of the offset zone is different from 2 cases. Then the white plus is showing on the bottom right panel here. So as you can see, the white plus it becomes larger at the trailing edge of the blades and the tip of the blades. So this is because the mesh we used at this area is not for Hex Mesh is not well refined, and so based on the mesh generated based on snappy mesh, it's not able to generate a good white plus for the turbulence model. So this is the problem we need to investigate, or we can solve it by using some mesh generation software like Pointwise or Saloon and something similar software. So move to next section about the results. So the test case with rotor speed with 12 RPM revolution per minute, and so the wing speed is 11 meters per second. So we compared the convergence on the Courant number. So there are 2 Courant number were selected here. So the first one is 0.5 and the second one is 0.3. So based on our numerical results, so convergence has been obtained for different Courant number. So their results between them are quite similar. I can't say it's identical. There's some difference here, but for the convergence state, so it's quite similar. Then, with the Courant number equals to being 0.3, we compare to the 2 different offset regions using these cases. So we also compare the numerical results compared with the COSA code from Lancaster, the in-house code from Lancaster, and the fast code based on boundary upper blade element method. So for the thrust, both numerical results be different from the results from COSA and fast, but the magnitude would be the same. And so maybe this is caused by the varying web class, and because the web class is slightly over, it's not evenly distributed on the blade surface. Then, but for the circular disk cases, the power generated by this rotating blade quite close to the fast code results. But for the body fitted zone, it seems to have a slightly difference from both results. And for the computational time to obtain the converged results, the circular disk it took maybe 511 hours, about 4.5 seconds in the simulation. And the body fatigue zone it used quite less computational time to obtain the converged results. So it's about 263 hours, and for the time if it's 2.5 seconds in the simulation. So even though with the body fatigue zone, the mesh seems to be the total mesh seems to be greater than the circular disk, but due to some interpolations, maybe for interpolations schemes and the stability of the numerical scheme, so the body fatigue zone could be earlier to obtain the convergence result. Then here's the ongoing work I'm going to show here, because in the objective of our research project is to develop an integrated model for floating offshore wind turbine. So in the integrated model, we need two offset zone here. One represents the rotating rotor here. The animation here shows a simplified model with a rotating like a box above the water surface here, and the floater is submerged in the water. So the wind blows from the left to right, so the entire body was pushed by the wind and moved backwards to the end of the tank. So here's some numerical results of like motions of the result. So as we can see from here, the surge, so it's moving away from the initial location, and then the rotor is rotating from minus 180 degree to 180 degree, and the pitch motion is generated by the vortexes just after in the rear side of the rotating boxes. So for the floater and the floater, they have same identical pitch angles. So it means our integrated model works for these complicated cases. So the conclusion, so the performance of overset mesh solver for aerodynamics on floating offshore wind turbine is examined, and the two different offset mesh zones are investigated in terms of accuracy and computational efficiency. So overset mesh solver is able to predict aerodynamics of a floating offshore wind turbine rotor and provides reasonable numerical results, although it still have some discrepancy in the comparisons. And next step, we're going to improve the mesh quality near the blade surface and with low and reasonable Y+. So approximately 30 for the work functions is a requirement for the work functions and is needed for the better accuracy. So finally, I would like to thank for the financial support from EPSRC projects. So first one is extreme loading on faults and complex environmental conditions. And the second is CCP on wave structure interactions. So it was introduced by Professor Groby from Plymouth University. So thank you for your attention. So any comments and questions are welcomed.
Thank you very much. That was a really fantastic presentation and some very interesting work. I see one question so far. What version of OpenFOAM did you use?
I'm currently developing the code in ESI version. The version I'm using is 1912, but I can compile code with some latest version.
Okay, that's fantastic. I don't see any more questions at this point in time, but we may have some time at the end of the session in case others think of some more questions. I noticed that our first speaker has been able to join us. So we will now revert back to where we would have started. And I'm going to introduce now Mr. Mohammed Najvan, who's coming to us today from the Indian Institute of Technology in Kanpur. And his presentation is going to be on the effect of different linear algebra solvers and dynamic mesh motion strategies on the flow field of a pitching foil. So at this point, I will hand over to you, and I'll see you in a little bit.
Yeah, thank you. Yeah. Can you hear me? Yeah.
Yes, we can hear you and we can see you.
Yeah. So good evening, everyone. My name is Mohammed Najwan. I'm from IIT Kanpur, India. So today I'm going to discuss the flow created by the flapping foils and the challenges involved in simulating such flows numerically. So initially, I'll give some insights into the background of the flapping foils and some of its application. And then I'll be discussing how I utilized OpenFOAM for simulating the flapping foil flows. So here I'll show how the effect of the choice of the linear algebra solver and the mesh motion strategies can affect the accuracy and quality of the numerical results. And towards the end, I'll discuss the interesting Quiescent flow condition and the problems encountered in simulating such flows. So if you observe in nature, we can see that all the natural flyers and swimmers, they use a flapping mode of propulsion. So inspiration from these can provide us insights in developing flapping vehicles like the flapping wing micro air vehicles or the robofishes. And in order to understand the dynamics of the flapping foil, it is essential to understand the trailing edge vortex patterns. So in the case of a bluff body, we can see that the vortices are arranged in such a way that they induce a velocity against the flow, and it is called a von Karman wake, and the body experiences a drag. Now, if the body flaps beyond a certain frequency or amplitude, the vortices switches its orientation, and it is known as the reverse von Karman wake, where the body experiences stress due to the velocity induced in the direction of the flow. So flapping foil flows are mainly characterized by reduced frequency or the Strouhal number. And with change in these parameters, we can observe different wake patterns with different dynamics. And another interesting phenomena observed at a higher Strouhal number is the deflection of the symmetric wake. And here, along with the thrust, there is a finite amount of lift as well generated, and which is exploited by the natural beings for maneuvering techniques. So we can see that several experimental studies have been conducted in this area. However, experiments have their own limitations. So numerical studies are quite essential. So now let's see how such motions are numerically simulated. So to begin with, we have considered a similar 2D rigid foil, which is sinusoidally pitching at the quarter-chord point. And this airfoil is kept in a medium with a free stream, constant free stream velocity. And we have used a computational domain of topology, and the radius of the domain is chosen such that it eliminates any undesirable effect of the boundary. And we have used a constant free stream velocity at the inlet, atmospheric pressure boundary condition at the outlet, and the moving foil is considered as a moving wall with zero normal flex. And the mesh we have used is a fine structured mesh with almost 0.5 million grid nodes, and we have conducted a grid and domain independency test for choosing the domain and the grid. And the governing equation is solved using the finite volume method. And since here we are dealing with a moving mesh, which may induce some additional flexes to the flow. So this is taken care by the ALE or the arbitrary Lagrangian approach, where it subtracts the mesh velocity from the Navier-Stokes equation. And coming to the flow solver, we have used an implicit Euler scheme for temporal discretization, and the time step is varied by a maximum Courant number method. And special discretization, we have used a second order accurate, and we have used the Pimble scheme for pressure velocity coupling. So now I'm going to discuss how the choice of the linear algebra solver is important. So when we discretize the computational domain on all the grid nodes, so it results in a set of linear equations and a sparse matrix. So in order to solve this matrix equation, we have to adopt an appropriate linear or iterative matrix method. So first we have considered a solver where we solve the pressure equation using this preconditioned conjugate gradient method with the diagonal incomplete Cholesky preconditioner. And here we have solved the velocity equation using a stabilized precondition by conjugate gradient method with the diagonal incomplete LU preconditioner. So when we visualize the flow, we observed a unphysical phenomena where the wake completely oscillates as a rigid body and a frequency which is not equal to the flapping frequency, and which is a complete unphysical phenomena. And if you look at the interface, we can see that the vortices are shearing, which is clearly unphysical. And we believe that it is an artifact of the linear algebra solver. So in order to confirm that, we tried the same experiment or the same simulation with a different set of solver, where we use where we solve the pressure equation using a generalized geometric algebraic multigrid method with Gauss-Seidel smoother, and velocity equation we used smooth solver method with symmetric Gauss-Seidel smoother. And here, when we visualize the flow, we could see that this set of solver could eliminate those unphysical conditions. And if you look at the interface, we can see the vortices clearly passing the interface. So we can say that while choosing a linear algebra solver, especially dealing with such kind of problems, one has to take extreme precautions in ensuring that if there are any similar unphysical oscillations, especially when dealing with small amplitude flapping motion where such oscillations are difficult to detect. So since we are dealing with a moving mesh, an appropriate mesh motion strategy is essential. So let's see how different or the choice of a mesh motion strategy can affect the quality of the result. So for this particular study, we have used three different mesh motion strategy. The first one is a solid body AMI. Here, the complete domain is divided into two parts. One that rotating part, which is surrounding the airfoil, and rotating the same kinematics of the airfoil, which is called as rotor. And we have an outer stationary domain, which is called stator. And these zones are separately meshed, and we couple them at the interface using the cyclic AMI condition. The next one is the displacement Laplacian method. Here, the complete here we have only one single cell zone. We don't have two separate zones. And here the mesh deformation or the mesh interpolation or the mesh morphing is happening throughout the domain. And the deformation is controlled by a governing Laplacian equation. And here we can change the degree of diffusivity for our requirement, like the extent of deformation we need. And the next one is interpolated solid body motion. Here also we have a single cell zone, but divided into two regions similar to solid body. One region which is rotating around the airfoil, and the other region which is towards the boundary and which is static. And this rotating region is again divided into two sub-regions. One is the rigidly rotating part around the airfoil, and the deforming part between the static and rigid part. And here the mesh motion interpolation or mesh morphing is happening only in the inside rigid part, or the unlike the displacement Laplacian. And so it is important to choose a strategy based on the requirement of the problem we consider. So the main advantage of the solid body AMI is that there is no relative motion between the mesh. So it can handle large flapping amplitudes without any mesh quality issue. But on the other two methods, a large deformation can induce numerical errors due to the mesh distortion. So the advantage of the other two mesh motion strategies over the solid body is that since we can control the extent of the mesh deformation, these strategies have more independencies choosing different types of problems, like fish schooling or a tandem flapping, where we employ more than one foil. So in order to see how these strategies affect the quality of the results, so we have compared it with some of the existing experiments. So here it is a case where we observe a 2p wake. A 2p wake is a condition where a two pair of vortices are shared in a flapping cycle. So when we compared this with the solid body AMI and the displacement Laplacian, we got a very good agreement with the experiment. But however, this interpolated solid body couldn't capture the 2p perfectly, and we observed a deflection in the wake, and which is clearly unphysical. So and we have also compared the results with some of other experiment simulation quantitatively, and here in this study we observed that up to reduced frequency of like 9, we observed a very good match, but beyond 9 the results were deviating. And a similar trend was observed in another study where above the Stahel number of 0.45, we observed a deviation. So we can say that we need to refine this linear solver or the mesh motion strategy more and more for getting a better quantitative match at higher frequencies. So till now, we have seen how the vortices change in the presence of free stream from a drag producing or a thrust producing or a deflected wake as we increase the Stahel number. So it would be really interesting to know for a limiting case when the Stahel number is infinite or at zero free stream velocity. A similar phenomenon is observed in the hovering of hummingbird, where we can say that it stay afloat in a single position without moving by just flapping its wings. So at this condition, an interesting phenomenon is observed. So where this jet is switching continuously either up, either down, or in a center line. It's like switching. So one school of thought believed that this switching is happening in a quasi-periodic way, but another study showed that this is happening randomly. So it is essential to know how does this switching happen and how we can control it to make use of this interesting phenomenon. And since there are like limited experimental studies and experiments have their own limitations, so we thought this problem can be addressed using simulation. So what happens when we systematically reduce the free stream from 1 to 0? So we can see that in the presence of free stream, the vortices roll up to discrete patterns and they convex away or convex downstream. But when we gradually or systematically reduce the free stream velocity, we can see that this vortex, they won't convex away, and they interact with each other to form complex or chaotic wake patterns rather than an organized vortex state, which we observed in the case of free stream. So this makes it harder to analyze the dynamics of the Quiescent flow. We can see that the dynamic continuously changes with an aperiodic pattern. We are getting different wake patterns. So to establish this, so we conducted a test where we simulated a case multiple times, keeping all the kinematics, initial conditions and boundary conditions same. And what we observed was we obtained different flow patterns at the same instant for different trials. So we believe that a small numerical noise, which can be even due to restarting the simulation, acts as an new initial condition, and they make the flow completely aperiodic, or they change the flow dynamics drastically. So this makes it hard to achieve the grid independence or time step independency. And since there are not many works available in literature where we observe a periodic pattern, like in the case of free stream, it is very difficult to validate the flow solver in the Quiescent flow condition. So to summarize the discussion, I'll go through the major points which I've discussed. So we saw how amazing is the flapping foil and why is it important to develop a like efficient numerical model to simulate such flows. And on that note, we discussed how the choice of an appropriate linear solver is really important, and and we saw the wrong choice of linear algebraic solver could lead to unphysical results, like we observe this wake oscillation. And then we discussed the importance of the mesh motion strategies, like we discussed how one can utilize the mesh motion strategies for the requirement of the problem, like a solid body where it can handle large amplitudes when we use large flapping amplitudes, or the displacement Laplacian interpolated solid body where we can have multiple foils, and solid body has its own limitation there. And towards the end, we saw the interesting Quiescent flow and the challenges faced in simulating such flows. And this is an area where a lot can be done. I mean, there are like several interesting problems still awaiting to be addressed. So I'd like to extend my gratitude to SCRB DST India for providing the fundings, and HPC ITK for providing me the computational resources. And especially I'd like to acknowledge OpenFOAM Organizing Committee for granting me the bursary for this registration and giving me such a wonderful platform. Thank you very much. And now I'm open for questions.
That's excellent. Thank you very much. That was a really, really interesting and insightful presentation. There are a couple of questions already. The first one, what initially gave you the idea that the rigid rotation issue was coming from the algebraic solver and not the interpolation or the numerical schemes?
So actually, we tried changing the different numerical schemes already used without changing the linear algebra solver. Like we tried changing the mesh motion or different techniques, but every time we observe this wake oscillation. And the next time when we tried keeping everything same, and when we tried this, like when we changed the linear algebra solver to a new solver, and this flow, I mean, the unphysical problem was actually eliminated. So we thought that this has to be a problem with the linear algebra solver, because we kept everything same and we did a lot of tests keeping these things constant, and only the linear algebra solver was creating this problem. So that's how we came to the conclusion.
Excellent, thank you.
But I like to add, like we are doing more tests to confirm this issue actually.
Okay, a second question: have you studied jet switching of the wake?
Yeah, actually, we started with the jet switching problem, but like I discussed in the presentation that we are facing a lot of issues. Like the problem with jet switching is basically it's completely it's random. Like there are studies saying it's quasi-periodic, but there are other studies saying it's random, and all the studies are experimental, and experimental has its own limitations. So we tried using different we tried studying the jet switching in simulations. But the problem occurred was like it was completely aperiodic. And when we restart the system after running for like 10 cycles or 20 cycles, and we are getting a different flow field, because when we are restarting it, that is acting as a new initial condition, and we are getting a new flow field. So it is very difficult to analyze the jet switching in Quiescent flow condition. And that's why we believe that we need to improve the numerical modeling for studying in that Quiescent flow. And it's very interesting area. Like there are a lot of opportunities and there are a lot of area to be addressed in that section.
Excellent. I see that your co-author, Chandan Bose, has joined us. There are quite a large number of questions. Obviously, lots of people are very interested in your work. So I might suggest, as I have done in other sessions, that where we don't get to talk about all of the questions and answers, that this can continue in the discussion forum, which will stay active outside of this session. So I'll need to move on to the next speaker now, but there are more questions that you may wish to address, Mohammed, in the Q&A function. Yeah, and also, sure. I see some more questions have come in for the first speaker, who was Mr. Navjan. So you may like to address that. So thank you again. It was great to have you here with us. Yeah, so our next speaker is going to be Professor Mario Tomei, and he's going to speak about atmospheric boundary layer versus surface layer equilibrium physics, a review and CFD investigation for consistent, horizontally homogeneous for pressure or shear-driven flows. So it's great to have you, and I'll hand over to you now. Just remember to unmute yourself, Mario. I can see you, Mario, but you still appear as muted.
Okay, now it's okay. Sorry for this minute. Good afternoon to all, and thank you. So I will present my work. I'm sharing, yes?
I can see your screen, but it's appearing in the PowerPoint format. Can you turn it into presenter mode?
Okay,
perfect.
Now I think it's...
That's excellent, thank you.
Now I think it's perfect, yes?
Yes, thank you.
So my work is about the atmospheric boundary layer versus surface layer equilibrium physics. So the problem is to address how can we model and use boundary profiles for boundary conditions that are physically and mathematically correct. So for this work, I use both OpenFOAM and ANSYS Fluent. I use also for Octave as ODA equation solver, but I will not present that software results here. So the goal is to obtain the very simple profiles for 1D, one-dimensional, the vertical direction of the wind profile in the atmosphere. And also for the simplest case, which is the neutral atmosphere, and for steady state using kappa epsilon, standard kappa epsilon model. So the atmosphere has the atmospheric boundary layer, which is 1 to 2 kilometers, 8, and the surface layer, which is about around 10% of that 8, which means 100 to 200 meters. In order to model the atmospheric boundary layer, we can assume different conceptual simplifications or assumptions. Also about the Coriolis force, which normally for local modeling is omitted, and the pressure gradient, which can be assumed to be 0 or not 0, etc. So I have here one paper that discuss all those questions, all those physical and also mathematical questions. So normally we want to have inlet boundary conditions that are horizontally homogeneous, and they have to be coherent with the model kappa epsilon standard in this case, or kappa omega, etc. And with the ground boundary conditions, which is a wall. In cities we have very high levels or very high heights of roughness, which can be between 0.1 meters or lower till 10, 20, 30 meters in very dense cities with high skyscrapers. So the most used inlet boundary conditions are those published by Fischer and Oxey in this paper. But those inlet boundary conditions are normally not well replicated by our other authors. This is discussed by Peter Richards from New Zealand, and he discussed a lot about this. And more recent papers from him discuss this. In this case, this other paper, which is from 2006, 2007, also discuss and address that problem. So in my work, I have been comparing and examining these two profiles, inlet profiles. Both are from Richards, Peter Richards, and they are summarized here. So in the first one, it is physically soundness to be applied to the surface layer, and the second one it is or can be physically accepted for higher heights till the atmospheric boundary layer 8. So the first one, the first set of boundary conditions, they are based on these principles. One very important is the third one, which assumes that the shear stress is constant in the vertical, which is an assumption, reasonable one, but it's reasonable only on the surface layer, not for the whole atmospheric boundary layer. So this first boundary set of conditions are based on, this in practical terms, are these very known equations for velocity inlet, for the turbulent kinetic energy, and for turbulent kinetic energy dissipation. The second set of equations, they are based, they assume other physical assumptions, namely that the shear stress in the atmosphere decreases linearly with 8. And if we solve the kappa epsilon equations, we get these results, which are here presented for non-dimensional units for turbulent kinetic energy and turbulent kinetic energy dissipation. And if we compare the velocity profile from the first equation, the first set of equations, which is here the equation number 1, and to the equation number 9 and 41, this is from the paper of Peter Fischer's 2015, we get very different velocity profiles. So I recommend, if you want to know more about this, to see this paper, which discuss with some detail these issues. So in the next 5 slides, I will present my work that intends to generalize those two set of equations. What I did is to assume different top boundary conditions at the top of the atmospheric boundary layer. I mean the value of the turbulent kinetic energy and the epsilon value, and those boundary conditions can be performed by Newman or by Dirichlet boundary conditions. So those 5 cases that I have here to present, this is the first one. In this case, the derivative of the turbulent kinetic energy at the top of the ABL is not the derivative, sorry, this is the turbulent kinetic energy. Non-dimensional value of turbulent kinetic energy is 3.33, and the derivative of epsilon at the top has the value of minus 2.38, and the shear stress in this case is considered constant. So this is equivalent to the Richard and Oxay paper of '93. So I have here different profiles for velocity, velocity simulated here, which is coincident with the velocity of RH93, because it's the same assumptions, and the velocity of Dave's and there is 78, and also the other variables, as you can see. The second case is different. So here the shear stress is linearly decreasing from the maximum at the ground till 0 at the top. So we get likely different value for the profile of the wind velocity and for other variables too. In the third case, I assume a value of turbulent kinetic energy of 3 at the top, and also the shear stress linearly decreasing, and we get these results. The case number 4. This case number 4 is similar to the Richards and Norris work. So it assumes a symmetry at the top. Symmetry at the top, it means that Newman boundary conditions, the derivatives are 0. And it also assumes that the shear stress decreases linearly from the maximum at the ground till 0 at the top. And finally, another case which assumes that the turbulent kinetic energy at the boundary top is smaller, 0.33 non-dimensionalized value, and the derivative of epsilon is 0. So we get higher, slightly higher velocities for the velocities in the curve. So these profiles that we developed here for one-dimensional, for the vertical dimension of the atmosphere, is very important to apply to complex wind engineering studies involving buildings or mountains. In this case, mountain, the flow field around the mountain, and finally, as conclusions, I can say that we developed consistent inlet profiles that assure horizontally homogeneous profiles for U, K, and epsilon. These new inlet profiles allows more physical assumptions, because we can consider different values of turbulent kinetic energy at the top of the ADL. These new consistent sets of inlet boundary conditions with the top values, Newman or Dirichlet boundary conditions for the top face of the domain, are indeed needed to use for in order to study ground obstacles such as mountains or buildings. The previous sets of boundary conditions were generalized in the present approach, and more detailed methodology will be published as a result of this work, namely the equations related with those profiles that I showed you before. And that's all. Only a small remark that I'm in Portugal, and today is our National Day, our poet Camões Day. Thank you very much.
That's fantastic. Well, happy Camões Day to you, Mario. It was great to have you joining us today. Thank you very much. I see one question here in the Q&A function for you. What kind of wall function did you use in these models?
Hogness functions. I'm not sure if I'm being enoughly specific. So the ground is not smooth. It's Hogness wall functions for the kappa epsilon available on ANSYS and on OpenFOAM.
Okay, I don't seem to have any other questions at this time. As always, the discussion forum is open and available for any further questions, and it is available outside this live session. So even once this session has concluded, you can still continue conversations there. I can see that there were some very active conversations going on, lots of questions and answers. So thank you all for engaging. I hope you all enjoyed today. I think that is our final session for today.